Right, so hello everybody. My name is Siggi Jonsson. I'm an Android engineer at Tinder, and today I wanted to talk about modularization and share some techniques that we've been using at Tinder to untangle our dependency graph. So modularization has been a hot topic in Android for a while, and our journey started, like many others, with a single app module that was getting too large and we wanted to break that up. So our initial attempts at modularization started with extracting layers. We called them domain and data. And the aim was to get separations of concerns by extracting business logic into domain and push the implementation details, so your data stores and network logic, into what we call the data module. It didn't take long until we wanted to get some of the same benefits from modularization and apply them to our actual feature works. So we called those modules UI modules. And we started to extract more and modularize our code base more, but now by feature instead of by layer. But we did actually quite like the layers that we had in place and the separation of concern that they enforced. So we ended up doing our modularization by feature, but also by layer. So it ended up with a structure that looked a little something like this, where we had at least 3 modules for every feature almost. So this was our strategy for a long time. And over time, we started to modularize more and more of our code base. Going back as far back as 2017, when things started, until today, in 2022, when about 20% of our code base is modularized. So the blue line there, the blue area at the bottom, shows how big of a percentage of our entire code base is in our monolith or application module. So this brought about great benefits. We're seeing faster iterations, better performance, isolation between teams, and so on. But at the same time, we're seeing pretty rapid growth in the number of modules in our code base. And we're seeing some issues with that. So there was overhead, and while improvements in Gradle, like configuration cache, helped a lot and brought about great improvements, there was still some overhead just from the amount of modules that we had in our project and navigating that, onboarding people into that. It was creating overhead, so we knew we had to do something about it. And maybe more importantly, we saw that the number of dependencies, so the blue line there at the bottom is the number of modules, and the number of dependencies is the green line. It was just growing at a much faster rate than our modules. So this was kind of our first hint that something had to change and we couldn't sustain this for much longer. So taking these data points into account, we knew we had to come up with a revised strategy. We really went back to the drawing board and started to ask ourselves why we were modularizing in the first place and what was the primary goal there. We decided that the main thing we wanted to optimize for was for the feature module independence. So we wanted to isolate the UI work, the features, your view code to a degree possible, and optimize for the speed of executing in those areas rather than other areas. So long story short, we decided to simplify our structure and our strategy and adapt this 3-layered structure with an app, feature, and library layers. And this is in line with current recommendations for modern Android development. And the key thing here is that features cannot depend directly on other features. And this is very important. And while we did want to keep it simple, we decided to include an extra layer. So we got 3 + 2 layers, and we added explicit public and internal modules to both the feature layer and the library layer. We did this both to support our existing dependency inversion practices and to better support the migration from the previous patterns over to this new structure. The key idea is to allow features to depend on abstractions and not be bothered by the implementation details. I won't go into all those details, but this is the gist of it. So here the feature can depend on a public library, and then it's the app's job to find the bindings and provide those dependencies at runtime for the app. Anyways, now that we've figured out why we wanted to modularize, we figured out what we wanted the structure to be like, now came the hard part. We didn't have a magic wand that we couldn't automatically migrate all our 700 modules at once and adhere to those same rules that we had put in place. So we knew that we had to put in some guardrails, and we needed to find some strategies to help us answer where we'd start, where we'd get the biggest productivity gains, our biggest return of investment from migrating things over. So luckily for us, we quickly came across a Gradle plugin called GraphAssert. And GraphAssert allows us to automatically validate our dependency graph. So it allows you to specify rules about which dependencies you do allow in your project and which you don't. So using the GraphAssert module, here we've restricted libraries from depending on features. We've restricted public libraries from depending on internal features, or internal modules, sorry. And we restricted internal modules from depending on other internal modules. So this means that if anybody tried to add a dependency that was not in line with our current rules, it will fail in CI. Additionally to the restriction of the rules, you can set a maximum height in the GraphAssert plugin. So the height represents the longest path through your build graph. So if you think about the modules that Gradle will have to build in sequence, the longest such sequential path is what's described as the height. And you can set a maximum height, and this means that you get a baseline, and if you add a module or a dependency to the longest path, you can fail, and you can go and look at what's happening there. Our usage of GraphAssert doesn't stop there. So GraphAssert can generate statistics about your module or about your project. And here we've run the task to generate the statistics, and we can see that there are 598 modules in the graph with 4,389 dependencies between those modules. And the current height is at 24. And it also shows you the longest path that we've shortened there in the slide. It shows you the longest path through your module graph. And so you can use this information to go and look at that longest path. Maybe that gives you some hints about what you could or should optimize. GraphAssert has an additional step that can be very helpful, and that is that it can generate a graph description language representation of your module graph. And this can then be taken and put into tools like GraphWiz, where you get a rendering of your current project graph. So we were excited to try this out. And the idea is that you can get a picture that looks like this, showing you the breakdown of your dependency graph and showing you in red the longest path through your dependency graph. But for large projects like we had on our hands, unfortunately, the output looked more like this. So, which isn't very useful. So we started to wonder if there was a better way to look at our graph and analyze what was going on. So that's when we learned about a cool tool called Gephi, which is an open source visualization and exploration software for all kinds of graphs and networks. Like we just saw, we can describe our project or module structure like a graph. So we can fire up Gephi, import the graph from the GraphAssert plugin, and right out the gate, we get, again, something like this, which still isn't super useful. But by applying a little bit of graph theory and using the built-in tools in Gephi, you can quickly go from this to something like this, which maybe still looks confusing and just looks like a blob of stuff. But what we've got here is not a static rendering, but a dynamic visualization of the entire project. Every node or every circle in the graph represents a Gradle module, and the lines are representing dependencies between the modules. So using this tool, we can traverse the graph, we can zoom in and out, we can find the app module there at the top, and we can even see the thin red line from the GraphAssert plugin representing the longest path through our graph. We zoom out again, and we zoom into a different corner of the graph. We can get a better understanding for how things are connected and what modules are part of our longest path in our graph. And if we zoom back out and we highlight that big node in the center, we can see how it is connected to various different parts of the graph. And it's not hard to imagine how such a central module could start causing problems as it grows and starts to impact more and more parts of your application. But before going into more details about the insights that this can provide, it might be helpful to take a step back and look at some graph theory. So graph theory is just the study of graphs, and there are standardized metrics that can be used to describe different characteristics of graphs. So one such statistic is what's called an in-degree. An in-degree of a node describes how many dependencies or how many arrows are pointing into a particular node in a graph. And using Gephi, we can calculate this metric for our dependency graph. And we get a nice graph showing us the distribution of the in-degree of all the modules or all the modules in a project. Similarly, there's a metric called out-degree, which shows how many dependencies are going out of each module or node in your graph. And again, Gephi can run these statistics, show us the distribution. And you can see an outlier there to the far right, and that's our application module that has on its own over 400 dependencies on other modules. Degree is the aggregation of those two, so it shows how many related modules either going in or out of a particular module. Get a distribution for that as well. Then there's something called modularity class, which is an algorithm that detects communities in your graph. And in our graph, it has detected 7 different communities, so those are modules that somehow are closely related or live close together in the graph, which can be quite interesting to see, and we'll see how we visualize that. We can see how we use that to visualize our graph. A final stat I'd like to share, and this is probably what I think is by far the most interesting, is a metric called betweenness centrality. So in graph theory, betweenness centrality is a way of detecting the amount of influence a node has. And it can be used to find a node that's acting as a bridge from one part of the graph to another part of the graph. And in the picture there, the nodes that have the highest betweenness centrality are the ones in blue or dark blue. And you can kind of see how those are the nodes that get called out are those that are at the center or at the heart of your dependency graph. You can think about it, how much transitive complexity a module adds to other modules. So here the blue node in the graph is the only reason why the nodes on the left know anything about the nodes on the right. So again, Gephi can calculate this metric and show us the distribution across our entire dependency graph for all the modules in our app. And putting these metrics into action, we can ask Gephi to color our graph based on the modularity class. We can have the node size be represented by the betweenness centrality of the nodes, and we can use a graph layout called Force Atlas that renders the graph and turns it from this into this that we can then start navigating and reasoning about. And the most interesting insight we found was when inspecting the big nodes in the graph, the ones with a high betweenness centrality. Because it turned out that those correlated with modules that we already knew had maybe too many responsibilities, had unclear boundaries, and just modules that overall had an outsized impact on things like build times in a project. So again, back to the highlighted node with the highest betweenness centrality. It not only has a lot of connections, but its connections are also big, which really shows how problematic areas can cascade through the dependency graph by adding what seems maybe in a PR as a simple one line. You're just adding a module as a dependency. In reality, it can have really big impacts. So when I was putting all this to use, we started to capture the metrics and acting on them. We now had actionable insights with measurable results, and we started to capture and report on the height of our modules in a graph, and we started to capture and report the betweenness centrality and some other module statistics. We started working towards reducing both of them and prioritizing the ones with the highest height and the highest betweenness centrality and trying to optimize those. And we couldn't have engineers rendering graphs all day, so we started to capture these metrics as part of our CI and track changes over time. And here you can see a graph that shows how we've been able to actively reduce the height of our module or like of our application over time by focusing on these metrics and optimizing them. Similarly, we've been able to focus on reducing the between centrality of some modules. So we're reducing the impact or the influence these modules, often problematic or legacy modules, have on the entire build graph. And by measuring those and tracking them over time, we're able to objectively say that a particular change actually made things better. And because the modules don't exist in a vacuum, we can actually see how an improvement in one area on one module can cascade across multiple areas of the code base, reducing this metric across many modules. So again, by putting this graph theory to use, we've been able to simplify our build graph, we've improved feature isolation, and we've improved library cohesion, which has resulted then in a simpler project, faster builds, and just overall happier engineers. Dramatic pause. So, okay, maybe you're looking at all this and you're thinking, what if we haven't gone completely mad? We don't have this many modules in our code base, but we're still having maybe modularization issues. So to figure that out, we thought it might be helpful, instead of focusing on the dependency graph that we have at Tinder, we thought it might be useful to do a case study. So using the newly published Now on Android repository as a case study, we decided to use these tactics, use these strategies to see if we could get any insights. And if you haven't checked this library out already, I'd highly recommend it. It has some great compose examples and other good practices, as well as being pretty heavily modularized, which made it a good candidate for our case study. So the first thing we do is we apply the graph as our plugin, add it to the build.gradle file. Step 2 is generating the statistics. We can see that for the Now on Android project, they have 14 modules, which is a bit less than we had, and they have 39 edges or dependencies between modules in their project. Their height is not bad at all. It stands at 4, and then we can see the longest path through their graph, from app to feature author to core data to core database, and finally core model. Well, we don't need to stop there. We can generate the graph file using the command here, and we see part of the output that's generated there. We plug that in to GraphViz, and this time around it actually renders something that's useful and we can look at and reason about. So there we can see how the red arrows are showing the longest path through the graph, and we can start getting some idea about how the project is organized, with the app module at the top. Next we see the 4 feature modules, and at the bottom we get what's been labeled as the core modules or the libraries that make up the project. So continuing our journey and using Gephi, we again open it up in Gephi and we're greeted with something like this. But remember, we need to do some work. We need to calculate some statistics before we can get anything useful from the Gephi tool. So we run the stats, and I've highlighted the ones that are relevant to us here. So we calculate the degrees, or the average degrees. We calculate the network diameter, and this is where metrics like between centrality come from. And we calculate the modularity, which is the third arrow there. So we run these, and we get an overview of the distribution of those metrics in the graph. From the modularity class algorithm, we detect 2 communities in this particular graph. And finally, the between centrality distribution starts to indicate that maybe we have something interesting going on here, with one outlier there to the far right. So again, working through the steps in Gephi, we adjust, we make the node color be represented by the modularity class. We make the node size in the graph be represented by the between centrality of the nodes, and we use the Force Atlas layout. And now we get something that's a little bit more useful. It looks like this. And we can see immediately how the graph is kind of split into 2 separate areas. And these are the communities. So you have the blue community, which is representing the features in the app and the app module. And then you have what's more the data processing side, the sync, the database, the networking gets detected as its own community in the pink area of the graph. And just by looking at this graph, we can start analyzing and seeing if we can spot any problematic areas. One thing that kind of jumps out immediately for me is we have one scenario, or well, we have two scenarios where the two features are reaching over into the other community into a module that's called core common. So this immediately jumps out, and we can go into Android Studio and try to figure out what's going on. And we've seen in our project, especially that vaguely named modules like common, they tend to turn into somewhat of a junk drawer and get too broad responsibilities that then creates problems down the line as these things start to grow and evolve. So again, looking at the core common module, we can look inside and see that there are two things happening inside that module. The first one, and I hope you can see some of that, the first one is a result class that is used by the features. And then the other one has something to do with the dispatcher, so the coroutine usage. And we can see from the usages of these two things that it's only the features that care about the result, while it's the data or the pink area of the graph that cares about the coroutine dispatchers. So this hints us at that maybe we have our first suggestion to optimize this project, and that will be to extract the result class into a core result module out of core common. And while this is probably excessive for a project of this size, but for a large code base with hundreds of modules and an ever-growing common module, this is probably a good idea to start doing. Next up, we zoom out again and we look at the entire graph. And we turn our focus to the biggest node in the graph, which is the core data module in the center there. And highlighting that one can help us understand why it has high between centrality. So we can see that it is connecting almost all of the modules or nodes in the graph. So the features are depending on core data, and core data then depends on all the other things almost in the project. And if we go and look inside core data, it looks like there are already some abstractions in place in that module. So we have repository interfaces, and it turns out that those interfaces are the only thing that the feature modules actually care about. But because they're implemented in line with their implementation details, you get this almost entanglement by the feature modules having to depend on core data to both know about the abstractions and know about the implementation details. So our next suggestion would be to extract the repositories out of core data into its own module. So we can split that up. And we could go on and discuss if it might be a better idea to split up those repositories by functionality or by feature, but we'll stick to doing it by layer for now. So to understand why splitting a library, which may sound counterproductive to optimize your build graph, maybe you'd want to reduce the number of modules. Let's take a look at the impact of maybe splitting a module like core data here. So what happens if we split the pink module there, representing core data, into two modules? So by splitting the module and pushing the dependency inversion boundaries up to the module level, we optimize the graph from the feature perspective, where they're able to just know about the repositories. They don't have to know about the implementation details, which was the intention all along. And more importantly, they're not exposed either directly or indirectly to the transitive dependencies or the rest of the complexities of the project. So in terms of build performance, this can mean that you don't have to recompile the feature module if some low-level database modules change. And you can avoid running expensive tasks like code generation if you only wanted to change the color or a string in a feature module and run some tests. So the second suggestion is to extract repositories out of core data. And this is exactly what we do. Using the magic of Keynote, we fast forward through the refactoring process of these two items. We can take another look at our graph after that change. We've extracted the repository interfaces into a module here at the bottom called core data public. And we've extracted the result class we saw earlier being in core common into a new module called core result. And now the features no longer need to know about core common. So looking at this updated graph, we can now see how only the core model and the core data public modules are sitting between the feature area and the implementation details. And if we look at this from, again, the perspective of the feature module, we can see what it knows about or what its dependencies are within the graph. And it only needs to know about the core model and the core data public. So only if those change will you have to recompile the features themselves. And looking back at the statistics, we can look at the new betweenness centrality and its distribution, and we can see, based on those numbers, that we've actually reduced the amount of influence any one node has over the entire graph. And so we can capture that data, and we have evidence for that our graph has been simplified. So now we have a new graph, and we can start the process again if we're still having problems with the complexity of our build system. The next step would be the task of looking into the sync module and still the core data, because they're still ranking the highest. So if we were going to go look for issues, that's where we'd start the next iteration. So there's one more thing. Because now that you hopefully have some visual reference for how these graph metrics can be useful and can help you find the problem areas in your code base, I figured we could share how we're doing it in our CI, skipping the insights because we don't want our engineers to be rendering these graphs and looking at diagrams all day. So here we're showing, and this is in a PR on the GraphAssert repository. You can go and look that up and take a look how we're doing that. And here we're using a library called jgraph to generate those insights or those metrics directly without going through the process of generating the graph, using the Gephi, running the statistics, so we can just run this one command and we can get the insights from our project. And here we're running it before we made the changes, and we can see that the highest ranked module in terms of betweenness centrality is core data. And after the change, we're running the same command again, and we can see that it's now the sync module that's the top ranking one, and core data is now second, and it's lowered its score dramatically. So hopefully this gives you some ideas on how you can start to capture these metrics and act on them in an automatic fashion. So to summarize, our recommendation is to flatten your dependency graph. You can use tools to visualize it like GraphAssert, GraphViz, and Gephi. We highly recommend you give this a shot and see what your project looks like. And we recommend that you capture and understand your graph height. And the idea is not to get your height to 0, which would be to push everything back into a monolith, but is to understand which modules might be unintentionally contributing a lot of complexity and adding a lot of overhead to your project and causing problems. And the same can be said about this betweenness centrality of the modules. So with these two insights in hand, you can start working on reducing the amount of these problematic modules, assuming you have problems. So again, the idea is not to drive everything to 0, but rather than to use these metrics to identify where you'd get the most value out of optimizing or where problematic areas in your code base might be. And yeah, that's pretty much all I wanted to share today. To wrap up, I want to give a special shout out to Iñaki, our build engineer at Tinder, to Joseph Raska, the author of the GraphAssert plugin, the Gephi team, and the jgraph team as well. So with that, I say thank you, and also we're hiring. Need to get that in there, and if you have any questions or would like to chat about some of these things or clarify some of these ideas, I'll be down afterwards at our booth downstairs. Thank you.